What is quality control? Quality control is a fundamental component of the quality trilogy, which also includes quality planning and quality improvement. Together, these processes form the backbone of effective quality management. To understand their roles, let's briefly explore each. Quality planning focuses on designing products and services that meet customer expectations. Quality control ensures that the planned quality is consistently achieved during production and delivery. Quality improvement, on the other hand, aims to elevate performance to new levels. Once improvements are made, quality control is essential to maintain these gains and ensure sustainability. This continuous monitoring helps guarantee that products or services meet specifications and align with customer needs, resulting in satisfied customers. So, what exactly does quality control entail? It begins with identifying what needs to be monitored, specifically, the key outputs and parameters that affect critical to quality (CTQ) requirements. Next, you must determine how these elements will be measured and monitored, including the methods, frequency, and responsible personnel. Performance standards must be established, which can be based on target values, specifications, or customer expectations. Then, actual performance is measured and compared to these standards. If discrepancies arise, corrective actions are taken to bring performance back in line. This process is supported by various tools and techniques such as control plans, measurement system analysis, inspections, and statistical process control, SPC, charts, among others. Consider a practical example: a grocery store known for its quick checkout service, promising that customers won't wait more than 5 minutes. To ensure this, the control subject might be the number of customers in the checkout line. The measurement unit is the number of customers waiting, monitored visually by the checkout clerk whenever a new customer arrives. The performance standard is set at no more than 2 customers waiting. When a third customer joins, the clerk alerts the manager, who opens another checkout line, thereby ensuring the wait time remains minimal. This systematic approach to quality control can be applied across various contexts, from manufacturing products to managing service-level agreements, SLAs, underscoring its universal relevance. Quality metrics. Quality metrics are essential in assessing the performance of products and services, often including measures such as defect rates, rejection numbers, failure rates, SLA, service level agreement, compliance percentages, and NPS, Net Promoter Scores. While these metrics are valuable, they tend to focus on the final outputs and are considered lagging indicators, revealing issues only after they have occurred. While understanding these outcomes is crucial, relying solely on lagging indicators limits the opportunity to make proactive improvements. A more effective approach involves integrating leading indicators, metrics that provide insights earlier in the process, allowing for adjustments that can positively impact the final quality. Quality management shouldn't just react to outcomes but should proactively ensure quality through design, prevention, and control. To achieve this, it's important to incorporate metrics that assess the quality of the design phase and those that monitor and control inputs, key variables, and process parameters that influence the final product or service. Input metrics could include measures of supplier process capabilities, the quality of raw materials, and compliance with specifications, such as tensile strength in materials or SAT, GMAT scores for incoming students. Metrics during processing might track characteristics like dimensions in manufacturing or call handling time in service industries. These can be expressed as percentages meeting specifications or through process capability indices like CP and CPK, which offer a deeper analysis of performance against standards. Clear operational definitions are crucial for these metrics, ensuring consistency in measurement and evaluation. This involves defining what is measured, how it is assessed, and the criteria used, supported by reliable measurement systems. For instance, in determining percent defective, clarity is needed on what constitutes a defect. Metrics should be traceable to critical to quality (CTQ) requirements, aligning with customer expectations. For example, maintaining the correct temperature for baking a pie impacts crust quality, which directly ties to customer satisfaction. Valid measurement systems ensure that data is reliable, regardless of when or by whom the measurements are taken, emphasizing the importance of calibration and measurement system analysis (MSA). Quality metrics provide a standardized language for measuring and reporting quality, and the significance of using appropriate metrics and accurate data in quality management cannot be overstated. Measurement systems evaluation. The principle of garbage in, garbage out holds true for quality-related data. Ensuring the data you use is accurate is crucial, which is why evaluating the measurement system is so important. A measurement system encompasses everything involved in gathering and recording data: sensors, instruments, gauges, methods, procedures, human appraisers, and operational definitions. When measurements are taken, the variation observed includes both the actual variation in the parts being measured and the variation introduced by the measurement system itself, known as measurement error. Ideally, the error introduced by the measurement system should be minimal, so that the observed data closely reflects reality. In practice, some degree of measurement error is inevitable, but it should ideally account for less than 10% of the total observed variation. Measurement system errors can be divided into those related to location, such as bias, stability, and linearity, and those related to spread, such as repeatability and reproducibility. Bias refers to the difference between the average measurement and the true value, and can often be corrected through calibration. Stability, or drift, refers to the consistency of measurements over time, and can be monitored using control charts. Linearity involves differences in measurement accuracy across the operating range of an instrument. Spread-related variations, on the other hand, include repeatability, how consistently one appraiser can measure the same part using the same instrument, and reproducibility, which refers to the consistency of measurements between different appraisers using the same equipment. These variations can be assessed through measurement system analysis, MSA, which involves studies like gauge R&R for continuous data and attribute agreement analysis for categorical data. Accurate measurement is the foundation of quality management. If the measurement system hasn't been validated, it's essential to conduct an MSA study first, and if necessary, make improvements before relying on the data. Without valid measurements, any analysis or conclusions drawn will be flawed, reinforcing the old adage of garbage in, garbage out. Process capability. Football enthusiasts know the critical role of the kicker: to score by sending the ball between the goalposts. If the kick misses the target and falls outside the posts, the kicker's performance will be scrutinized. However, if a kicker frequently misses, it's worth questioning their ability. In quality management, this scenario parallels assessing process capability. Process capability measures how well a process produces outputs within set specifications. Imagine the goalposts as the specification limits. The left post represents the lower limit, and the right post, the upper limit. Ideally, the process should consistently produce results between these limits. To measure process capability, we use several metrics. First is potential process capability, denoted as CP. CP compares the specification range to the process spread. It's calculated by dividing the specification width, the difference between the upper and lower specification limits, by the process spread, which encompasses 6 standard deviations or 99.73% of process variation. A CP of 1.0 or greater indicates the process might meet specifications. Less than 1.0 suggests otherwise. Essentially, if the width of the goalposts exceeds the process spread, the kicker has a potential to score. However, what if the kicker's aim is off-center? This is where process shift comes into play. To measure actual performance, we use the Actual Process Capability Index, or CPK. CPK considers how the process mean aligns with the specification limits. It includes CPU, the capability to avoid exceeding the upper limit, and corporal, the capability to avoid falling below the lower limit. CPU is calculated by dividing the distance between the upper specification limit and the process mean by half the process spread, 3 standard deviations. Similarly, corporal is calculated by dividing the distance between the process mean and the lower specification limit by half the process spread. CPK is the smaller of CPU and corporal, and it indicates the actual capability of the process. A CPK of 1 or greater suggests that the process is capable of meeting the specifications. CPK is never greater than CP, with the ideal scenario being when CPK equals CP, indicating the process mean is perfectly centered. For continuous data, statistical software like Minitab can perform process capability analyses. For attribute data, such as defect counts, metrics like DPMO, defects per million opportunities, are used. Minitab also supports binomial process capability studies for such data. When conducting these studies, ensure the process is stable and in control. Reliable process capability analysis requires a substantial dataset, ideally at least 25 subgroups with a total of 100 or more data points. This approach helps accurately assess how well the process meets specifications, much like evaluating a kicker's ability to consistently score goals. Process control for those of us who drive, checking the oil level is a familiar routine. We use the oil dipstick to assess whether we need to add more oil and how much is required, ensuring it doesn't exceed the maximum line. If the level falls between the add oil line and the maximum, no action is needed. This straightforward tool, an oil dipstick, serves as an effective means of monitoring and controlling oil levels in our cars. It's a prime example of process monitoring and control. Imagine if your business processes could be monitored and controlled with such simplicity and effectiveness. The good news is that they can. Process monitoring and control are crucial for maintaining consistent quality and performance. Ideally, these controls should be managed by those directly involved in the work. To achieve this, a clear blueprint is essential, known as a control plan or process control plan, which outlines what needs to be monitored, controlled, and by whom. For instance, a bakery's process control plan might focus on oven temperature and baking time. Detailed instructions on developing control plans can be found in the Six Sigma Green Belt course. Training, standard operating procedures, SOPs, and detailed work instructions are crucial for implementing the control plan effectively. Moreover, operators and managers need tools to determine when to intervene or let the process run its course. Statistical Process Control, SPC, charts, developed by Dr. Walter Shewhart a century ago, serve this purpose well. For successful process monitoring and control, several elements must be in place. Process capability. Ensure processes meet specifications to avoid chaotic interventions. Employee knowledge. Provide employees with clear guidelines on their roles and actions required. Control subjects. Identify and list appropriate control subjects in the control plan. Empowerment. Clearly define authority, responsibility, and accountability in SOPs and work instructions. Skills and training. Ensure employees are skilled and their training is up to date. Management support. Equip managers and process owners with necessary resources and tools. Behavioral alignment. Align performance metrics and rewards with organizational goals and priorities. Process monitoring and control are vital for maintaining process performance and quality. By leveraging control plans, SOPs, work instructions, and SPC charts, managers and operators can effectively manage these crucial aspects. Statistical Process Control, SPC, Imagine you're not a chef, but you've been asked to monitor food cooking in a frying pan. How do you know when to stir the food or let it be? This is similar to how statistical process control, SPC, charts work. Developed by Dr. Walter Schwart at Western Electric, SPC charts are tools used to help production managers decide when to halt a process due to defects and when to let it run despite random variations. These charts guide operators and process owners by highlighting when intervention is necessary and when to allow the process to continue uninterrupted. SPC focuses on understanding process variation, which falls into two categories: random and non-random. Random variation is due to chance or common causes inherent to the process, such as poor design, methods, training, or supervision. If only common causes are present, the process is considered to be in control. Non-random variation, on the other hand, arises from sporadic or special causes, unexpected issues like equipment malfunctions, broken tools, contamination, or untrained workers. When these special causes occur, the process is deemed out of control. SPC charts are designed to detect these special causes so they can be addressed and corrected. SPC charts plot various process metrics, such as product dimensions or defect rates, over time. They typically feature a center line representing the average value and control limits set at 3 standard deviations above and below this mean. For example, an individual chart, iCert, displays 50 observations of a characteristic, with the control limits indicating the boundaries of random variation. With a 99.73% probability of data falling within 3 standard deviations, any points outside this range signal non-random issues that need investigation. It's important to note that SPC charts are not related to specification limits or customer targets. They reflect the process's inherent behavior and random variations over time. If the control limits are not satisfactory, consider initiating a quality improvement project, such as Six Sigma, to reduce variation and enhance process performance. Process control versus process capability. A process is considered to be in control when it exhibits only common cause variation, meaning no special causes are influencing its performance. If special causes are present, the process is deemed out of control. Statistical process control, SPC, charts track variation in the process, aiding in the determination of whether the process is in control. Control limits are determined based on actual process behavior, not by personal preference. They reflect the natural voice of the process. Conversely, process capability evaluates how well the process meets specifications, which are derived from customer requirements. By comparing process variation to specifications using histograms, you can assess how well the process aligns with these standards. A process with a capability index, CP, of 1 or greater is considered potentially capable, as the specification width exceeds the process spread. It's important to distinguish between process control and process capability, as they are not the same. To illustrate different scenarios, consider the following diagram of process control versus capability. In the top left quadrant, a process is both in control and capable, which is the ideal scenario. The process spread is narrower than the specification limits, ensuring high-quality performance. If the spread is wide but still within the specification limits, monitor the process closely to keep the mean on target. In the top right quadrant, a process is in control but not capable. This is akin to driving steadily but in the wrong direction. The process is stable but not meeting specifications. This quadrant presents two scenarios. If the process spread is small but the mean is off target, the process still produces defects. For example, a car consistently hitting the side of a large garage indicates poor aiming. If the process spread is larger than the specification width, such as parking a truck in a small garage, Quality improvement efforts like Six Sigma DMAIC should be implemented to reduce variation and align the mean with the specifications. The bottom right quadrant represents a process that is both out of control and not capable. Immediate action is required to address special causes and reduce variation through quality improvement projects. This scenario, while challenging, represents a significant opportunity for improvement. Finally, the bottom left quadrant is where the process is out of control but not considered a viable scenario for capability, as an out-of-control process cannot be capable by definition. This quadrant serves as a conceptual reminder of the relationship between control and capability. Your goal is to bring the process under control, minimize variation, and improve its capability to convert an in-control process into a highly capable one. Inspections, testing, and audits. Imagine you're dining out at a restaurant and, after a wonderful meal, you receive the bill. Do you double-check to ensure everything is accurate? That's a form of inspection. Just like checking the bill, inspections in quality management involve verifying that products or services meet the specified requirements. This process, along with testing and audits, is essential in maintaining quality standards. According to the ISO 9001-2015 standard, inspection involves assessing whether specific requirements are met. An audit, on the other hand, is a thorough, independent evaluation process designed to determine how well the criteria are being fulfilled through objective evidence. Inspections are focused on ensuring that products or services adhere to set specifications and can occur at various stages, including at supplier locations, during production, in-process inspection, or on finished products, final inspection. Depending on the criticality of the quality characteristic, inspections may be conducted using different sampling plans, from rigorous methods to full inspections. A notable example is when a black belt at a multinational electronics company I trained expressed concern that their final inspection station was no longer detecting defects. I assured him that his Six Sigma project had improved the process to such a high level, CPK of 1.33 or even 2.0, that the likelihood of defects was minimal, making further inspection unnecessary. Testing, which often takes place in laboratories, evaluates materials, components, or products against relevant standards or regulations. This could involve testing for hazardous substances, chemical composition, tensile strength, or crashworthiness. Meanwhile, audits provide a higher-level review of the quality management system itself. For example, a quality audit might assess whether the manufacturing process's inspections and testing are conducted correctly and if the quality system adheres to ISO 9001 standards. In summary, while inspections, testing, and audits each play distinct roles, together they help ensure that products or services meet the specified quality requirements.